Hello everyone, today we are going to discuss RSA cryptosystem, which is an important topic in cryptography. So in this video, we'll be learning about RSA algorithm, RSA key generation, and also the mathematical foundation needed for understanding the RSA algorithm. So first, let's know about RSA algorithm. So basically, RSA algorithm is used for data encryption and decryption. Assume that there are two devices which are communicating to each other. So if the device 1 sends a message to the device 2, any other device can interrupt into their communication and read their messages. So to avoid this, we will be using this cryptographic algorithms for data encryption and decryption purposes. So now the device 1 will be encrypting the original message and sending to this device 2, and the device 2 will be decrypting the ciphertext to get the original message. So by this way, the third person cannot read the original messages. So the second point says that RSA algorithms comes under public key cryptography. So we will be discussing this public key cryptography in the next slide. So and the RSA algorithm security so basically depends on prime factorization of the numbers is computationally hard. So we'll be seeing how this fact that prime factorization of large numbers is computationally hard, it will be deciding the RSA security. So now we will be seeing what is symmetric key and what is asymmetric key cryptography. So the main difference between symmetric key cryptography and asymmetric cryptography is in symmetric key encryption, we'll be using the single key for both encryption and decryption. But in the case of asymmetric key encryption, we will be using two different keys, one for encryption and one for decryption. And also note the point that asymmetric key cryptography is also known as public key cryptography. And also one more point is generally symmetric key encryptions are faster than asymmetric key encryptions. Now let's learn the basics which are required to understand RSA crypto system. So the first thing which we will be learning is modulo operation. So R equal to A mod B. These statements implies that R is a remainder when A is divided by B. As simple as that. So these are the four points which will helping in learning the RSA. So A mod n plus B mod n whole mod n can be also written as A plus B mod n. Similarly, A mod n minus B mod n whole mod n can be written as A minus B mod n, and also A mod n multiplied by B mod n whole mod n can be written as A multiplied by B mod n. And this last point is very important. You should remember. So A mod n whole power d mod n can be also written as A power d mod n. So these are the some important points about the modulus operation. And the next mathematical function we will be learning is Euler-Torsson function, which can be also called as phi of n. So for any number n, phi of n represents the total count of the numbers between 0 and n minus 1 that are relatively prime to n. So let us look into this example for better understanding. So let n equal to 10. Then all the numbers which are starting from 0 to n minus 1. So this n minus 1 is nothing but 10 minus 1, which is equal to 9. So all the numbers from 0 to 9 are 0, 2, 3, 4, up to 9. And the numbers which are relatively prime from the sets, this set to the number n are 1, 3, 7, 9. So what does this mean is, so after finding the complete set 0 to n minus 1, we have to find the numbers which are relatively prime to the n. So basically here it should be relatively prime to 10. So here we'll be checking is 1 is relatively prime to 10 or not. Is 2 is relatively prime is to n, which is 10 or not. So from this set 1, 3, 7, 9 are the only numbers which are relatively prime to 10. So there are total 4 numbers which are relatively prime to the number 10 in the set 0 to 9. So then the phi of n will be equal to 4. So now you got the basic understanding of Euler-Torsson function. It basically represents the total count of numbers between 0 to n minus 1 which are relatively prime to n. So these are some important points we should remember. So the first point is phi of p equal to p minus 1 if p is a prime number. It is obvious that p if a number is prime, all the numbers which are less than prime number are relative prime to p. So that's why it is equal to p minus 1. So for example, if we see prime 37, all the numbers which are from 1 to 36 are prime to 37. So that's why phi of 37 is equal to 36. And the second point we should remember is phi of p multiplied by q is equal to p minus 1 multiplied by q minus 1 if p comma q are prime numbers. So let us look into this example. So here phi of 21 has been asked. So phi of 21 is nothing but multiplication of two prime numbers 3 into 7. So by using this formula we can calculate the phi of 21 which is equal to 3 minus 1 into 7 minus 1 which is equal to 2. So these are this is the Euler-Torsion function. So now we'll be looking into Euler's theorem where we'll be using that Euler's torsion function or phi of n. So basically this Euler's torsion theorem states that a power phi of n mod n equal to 1 where GCD of a comma n equal to 1. So this condition always satisfies when the GCD of a comma n equal to 1. So we'll be looking into this an example. So let take an example of a equal to 3 and n equal to 10. So we know that for n equal to 10 phi of 10 is 4. So we'll be substituting the phi of n in this value and the a value as 3 here. So 3 power 4 mod 10. 3 power 4 is 81. 81 mod 10 is 1. So the theorem satisfies. So for every numbers which satisfies this condition where GCD comma a comma n equal to 1. So this Euler's theorem will be satisfying. Now let's look into the main part of the video, which is RSA algorithm. So as I already mentioned that RSA algorithm comes under public key cryptography. So in public key cryptography, we will be using two keys, one for encryption and one for decryption. So in this RSA algorithm, we will be going to through two phases. So the first one is key generation, and the second one is encryption and decryption part. So we will be assuming that there are two users. The first one is Bob, and the second one is Alice. So we will be generating the public and private keys for the Bob, and Alice will be sending a message to the Bob. So this is the scenario we are assuming, and let's now get into this algorithm. So the first phase is key generation. So in this key generation, we will be generating the public and private keys for the Bob, so that Alice can use the public key of this Bob to encrypt the message. And after Bob receives the message sent by Alice, so he can use his private key to decrypt the message. So first we will be seeing to how to generate these keys. So first we will be choosing two large prime numbers p comma q. So after choosing two large prime numbers, we will be computing n such that n equal to p multiplied by q. So it's simple. So n will be first selecting two prime number and we will be calculating n such that n equal to p multiplied by q. So since n equal to p of q, so phi of n, which is nothing but phi of p multiplied by q, will be equal to p minus 1 into q minus 1. So this point we already mentioned in the previous slides. That is phi of p and q equal to p minus 1 and q minus 1, where p comma q are primes. So if you forget, once go back to the video and once look at this point. So and the third point states the start step will be, so we will be selecting a number e such that e can be any number. So it should satisfy the condition such that GCD of e comma phi of n should be 1. So you can select any number e such that GCD of e comma phi of n should be 1. So in the fourth step, after calculating computing the e, so we will be generating another number called d. So where it should satisfy the condition ed equal to 1 mod phi of n. So that fourth step basically means, so we should find a d such that ed when divided by phi of n leaves a remainder of 1. So that's it. It's simple. So now after calculating the E and D, so now E will be our public key. So E will be public key of Bob. and D will be private key of this Bob. So these are the 4 steps which are involved in generating the keys for Bob. And next we'll be seeing how Alice is encrypting the message, and after receiving the message by Bob, how he is decrypting the message. We'll be seeing that now. So suppose Alice want to send a message to Bob. Suppose she wants to send a message to Bob. Then let us assume that the message be an variable M. So the encryption algorithm is nothing but C equal to M power E mod n. So we already know E is nothing but public key of Alice. So Alice is using the public key of Bob to encrypt the message M. So after using this formula M power E mod n, so we will get an ciphertext C. So now this Alice will send the ciphertext C instead of message M, so that the third person cannot read the original message. So also note that GCD of M comma N should be 1. So keep the point in mind that a GCD of M comma N should be 1. So we'll get to know why this condition should satisfy that GCD of M comma N should be 1. So and after Bob receives the ciphertext, he will use the decryption algorithm, that is M equal to C power D mod N. So when he substitutes the ciphertext in this algorithm, he will be getting the original message M. So Bob uses private key to decrypt his message. So we know that D is private key of the Bob. So since after getting the ciphertext, he will be using his private key to retrieve the original message M. So these are the encryption and decryption algorithms. Now we will be just looking at a solved example for better idea. So assume that Bob chooses the prime numbers are p equal to 3 and q comma 11. So in this example, I am taking this p comma 2 are small primes for understanding and for simple solving. So that we know that n equal to p multiplied by q. So now p equal to 3, q equal to 1. So n will be 33. And after finding n, so we will be calculating the phi of n, which is nothing but p minus 1 multiplied by q minus 1. So this will be equal to 3 minus 1 multiplied by 11 minus 1, which is in turn equal to 20. So and Bob chooses E such that GCD of E comma phi of n equal to 1. So I already said we will be choosing any E such that GCD of E comma phi of n should be 1. So we can choose 7 such that 7 comma 20 are relatively prime where their GCD is 20. You can choose another E value which if that satisfies this GCD of E comma phi equal to 1, then you can choose that E also. So in the next step we will be finding a D such that ED equal to 1 mod phi of n. So we will be finding a D such that when multiplied by E and divided by phi of n, it leaves a remainder 1. So basically we will be multiplying a number with 7 and we will be dividing it by 20 such that it should leave a remainder 1. So if you take D equal to 3, so 7 into 3 is equal to 21, and when divided by 20, the remainder will be 1. So here we can see that D equal to 3 satisfies this condition. So now the E equal to 7 will be our public key and D equal to 3 will be our private key. So coming to this encryption and decryption part. So now Alice sends a message. So now Alice want to send a message to the Bob. So let the message be M equal to 2. So to encrypt this message, so he will be using this encryption algorithm. So M power E mod n, which is equal to 2 power 7 mod 35. So E equal to 7, which we already calculated. So this will be equal to 29. So after calculating the encrypted message, so now Alice will send this encryption ciphertext to the Bob. So now the ciphertext is sent to the Bob. Now Bob uses this decryption algorithm to find the original message. So now he will be substituting the ciphertext here, 29 power D, which is his private key, which will here we calculate it as 3. So now 29 power 3 mod 33, which is in turn equal to 2. So the message equal to that the original message which as Alice was sent also equal to 2. So this is an example of RSA. So the question is, does RSA work for all the cases? So yes, RSA work for all the cases. We'll be looking how RSA work for every example. So we know that this is the encryption algorithm which we'll be using in RSA, and this is the decryption algorithm. So let us assume that so after decrypting the message, we are getting M dash. So we will assume that M dash is not equal to the original message. So we will assume this case and we'll proceed. And at last, we will be proving that this M dash is equal to M. And by proving that, we can say that RSA work for all cases. So yes, is M equal to M dash always? So now let's look into that. So from the decryption algorithm in the ciphertext place, we can substitute the encryption algorithm which we'll be using for getting ciphertext. So if the original message is M, so M power E mod n gives the ciphertext. So in the decryption algorithm, in the place of ciphertext, we'll be keeping this M power E mod n. So we will be substituting this M power E mod n in the place of C. So now in the second step, we can see that M dash equal to M power E mod n whole power D mod n. So we already know that we learned in this modulus operation in the starting slides. It is this can be written as M power ED mod n and whole mod n. And this and again this can be written as M power ED mod n. So this is modulus operation. If you forgot, you can go back in video and again look at the points which we discussed in the modulus operation. So now at this step we got that M dash equal to M power ED mod n. Now we should prove that this RHS is equal to M dash. So uh, so one point we should be remembering is, so we know that ED equal to 1 mod phi of n. So this is the condition for will be where we calculate the D. So this point states that ED equal to 1 mod phi of n. So basically we know that what does this means. So when ED is divided by phi of n, it leaves the remainder of 1. So that this point can be written as like this. So ED equal to k multiplied by phi of n plus 1. So here you can see that ED can be written as k multiplied by phi of n plus 1, because when k multiplied by phi of n plus 1 is divided by phi of 1, we get a remainder of 1 for any number k. So when divided by phi of 1, so this part will be leaves a remainder of 0, and this part will be leaves a remainder of 1. So we know that, so for any number k, we'll get the remainder 1. So in the place of ED, we can substitute k multiplied by phi of n plus 1. So here in the place of ED, we will be substituting this k multiplied by phi of n plus 1. So here in the step 2, we'll be substituting the ED value as k multiplied by phi of n plus 1. So this expression can be expanded like this. So m power k multiplied by phi of 1 into m. So we know that a power uh, x power a into x power b equal to x power a plus b. So using that exponential uh, formula, so we will be we used here to expand this. So after expanding this, we can further expand this as m power k star, I mean k multiplied by phi of n mod n and multiplied by m mod n. So we are again further dividing these two terms into separate modulus. So in the fourth step, so after separating into the m and m powers separately, we can write bring this power k outside of this whole mod n. So this in the fifth step we can write like this: m power phi of n mod n whole power k. So this can be transformed into this, and we know that if you recalls the Euler's theorem, a power phi of n mod n equal to 1, where GCD of a comma n is 1. So if you look at this, it is in the Euler's theorem form. So here is the phi of n and here is n, and we know that m will be taken such that GCD of m comma n is 1. So this satisfies the Euler's theorem. So that is why we learnt Euler's theorem in this video. So now this equation will be resulting into 1. So 1 power k in the sixth step we can see 1 power k into m mod n. So which will be we can write is m mod n. So m mod n is nothing but it is equal to m. So m dash equal to m, hence proved. So by looking into all these steps, we proved that m dash is always equal to m. So we can say that RSA work for any example. Is RSA really secure? So let's look into that. So generally public key is known to everyone. So the first point states the same. So the Bob's public key is known to everyone, that is n comma e. So if any sender who wants to send a message to Bob, he should encrypt the message using the Bob's public key. So if I want to send a message to the Bob, I will be using his public key, that is E, to encrypt the message. And after encrypting the message, I will be sending it to the Bob. So while sending, if any hacker, so if there is a hacker, he wants to decrypt the message which I send to the Bob, then he needs to know Bob's private key, that is D. So so I'm sending a ciphertext to the Bob. So if the hacker want to decrypt the message and read the original message, so he need to know the private key for decrypting the ciphertext. So if the hacker wants to know the original message, so he should definitely know the private key. If he needs to know the private key, then he needs to find phi of n, because ed is one mod phi of n. So if here hacker knows the value e, and if he wants to know the value d, he needs to know the value phi of n. So if he needs to know the value of phi of n, he needs to know the values of p comma q, since phi of n is p minus 1 multiplied by q minus 1. So since we know that phi of n is nothing but p minus 1 multiplied by q minus 1, if he wants to know phi of n, then he should know values p comma q. Then to find p comma q, the hacker needs to find the factors of n, since n is equal to p multiplied by q. So if the hacker wants to know the values p and q, then he needs because n is public to everyone, then he needs to find the factors to find p comma to know the values in p and q. But I already mentioned in the introduction slide that prime factorization of large numbers is computationally hard. So this means, so if we see, even though the hacker knows the value of n, he can't find p and q values, because finding the prime factors of a large number is computationally hard. Since he cannot find values p comma q due to the hard problem of factorization, then he cannot find the phi of n. Since he cannot find the phi of n, he cannot find the value of d. Since he cannot find the value of d, he cannot decrypt the message which I send to the Bob. So this is why RSS is secure always. So if you like the video, consider doing subscribe, and thank you for watching.